Are you trying already?
No.
So go through. It takes forever to just click a button.
I don't think it's slow. I think it's because like there's something wrong with the React functions or something. Because sometimes the page doesn't work. I don't know.
I think because we're using what Marcel did for our website, around the features like really Wait, what? We don't have the stream link on here. Oh. Okay, this is a big move. How many doors are in this place?
1, 2, 3, maybe 4. What doors is that?
Sleep outside?
Yeah.
So apparently we called it an in-person workshop and we have put it in the stream. So
You have a what?
we have apparently this event was labeled in person. So we don't have a stream one.
Oh, do you have trouble making it?
I'm trying to get it right now.
Okay, Todd Bacon's on there. Good for him. If you can hear me, Todd Mate, good for you. Are you distributing snacks at the end?
How did you say about that 60?
Yeah.
Okay.
That's what I always do. That's my.
Sure. So before we start, y'all, we have snacks and like drinks, I guess, refreshments for y'all. So if you want to get it before the workshop starts, run them out, or even during the workshop, we just have that in the front for y'all. It's so funny.
Didn't we only get like $20?
We got $30. See, we got a pizza. Then we realized some of the overhead.
Yeah.
Of getting delivered and doing all that.
Too much.
You think these people have more money?
Look at this dude. You're saying no. Where do you live? Stocks in life.
We'll come right now.
So we'd be nicer. This is our brand image at stake. Laugh, did not work hard to ruin it. One message. Hello, Lucas.
You can't even hear you too.
Unfortunately, no.
Okay, 701. I think you're good to go. I'll let you take a look.
I think it's done.
Well, it's hard to talk.
Oh, good luck.
Alright guys, give me like 1 second to set this up because it's kind of scuffed. Hi, yeah.
Oh, the snacks, yeah.
Oh, I think
Should I?
you're
Does this mic work?
Can you guys hear me?
Does it work?
Yeah, it works.
I don't want to hold it though. Oh my god. Alright, we're gonna start. Hello, thank you guys for coming out to another AIS production. Today we're gonna be talking about Introduction to Computer Vision. Forward, if you join that link right there, it'll let you access like a little website that lets you ask me questions. So you don't have to like raise your hand and then like, oh, ask you later, or like it's kind of awkward or you don't want to interrupt the thing. So you can just ask questions on there. I see them up here. I can answer them and stuff like that. So just make sure you join that. That's gonna be up the whole time. So who am I? My name is Aaron Chang. I'm the content director. There's my email. Write it down if you want to email me later. Content director, what that means is that I'm in charge of the people who will make these types of workshops in the future. So I'm presenting this myself, but you'll see many more projects from our content coordinators. My email is right there if you need any more contacts. I'm also on Discord a lot. So our agenda today is talking about what is computer vision. It's a word that's thrown out a lot, and like a lot of people don't know what it means. It's like the new equivalent buzzword of artificial intelligence and machine learning. Like now that people kind of know what that is, people don't really know what computer vision is, and that's what they're searching to. And then we're going to be talking about a library called MediaPipe Hands, and then we're going to be doing some American Sign Language detection and what goes behind that process. And then we're going to go do a demo at the end. So that's basically the whole agenda for our workshop today. So first up is the big question, what is computer vision? So the main thing is that it makes computers understand images. Computer vision is us trying to make computers understand images. Vision is about discovering from images what is present in the scene and where it is. That's the official definition. And the computer interprets images of a real scene that obtain information useful for tasks such as navigation, manipulation, and recognition. So these are the main tasks of computer vision and why we want to use computers instead of humans to do it. Because computers are vastly more superior and powerful and can do more calculations than any human could do in seconds for these certain tasks. So the goal of computer vision and what we're a part of in this is that we're there to bridge the gap between pixels and meaning. So if you know about images, it's composed of pixels with various color values and opacities and stuff like that. But how does a computer get meaning from those random numbers from 0 to 255 is that we have to make that correlation. So one major thing that we have to understand is what computer vision is not. It is not image processing, image enhancement, all those types of things. This is like We've seen Photoshop, where you see altering images or editing images to make them look good for your Instagram. And it's also not computational photography. This is things that's used in DSLR, such as, or if you have like a Google Pixel or an iPhone, it's like the night mode where you can take pictures in really dark places and it brightens it up. It's not that. Those use algorithms, explicitly programmed scripts that alter the image, and it's not really considered in the realm of computer vision. So why is computer vision important? It replicates human vision to allow a machine to see and interpret. That's the main point, is that it allows machines to interpret what it sees. And this is central to the problem of artificial intelligence, which is artificial intelligence is considered like the end goal is to create a person, a living being. And obviously one of those things has to be interpreting what it sees. And there's also many other industrial applications. And another reason is that we gain insight to how we see it as people. There's not a lot of research, or there's a lot of research done, but there's not a lot that we know about how humans see and how that corresponds to our eyes going to our brain and us understanding what we see and applying correlations. So that's another reason why we explore computer vision, is that maybe we can get insight on how we see the world around us. So here are some major applications for computer vision: intelligent machines, also known as artificial intelligence; industrial inspection. So this is things for like light bulbs or electronic circuits or like fruit or anything. Is to see anything from the batch that looks damaged or isn't ripe enough or was damaged has mold on it, or electronic circuit is not correctly soldered. Any things of that sort. Automotive uses: Ford, GM, DARPA Grand Challenge. The DARPA Grand Challenge is creating a moving robot that can move by itself. And there's also Tesla. So this includes self-driving. Also includes things such as like parking assistance or like any other features, any smart features of a car that helps you drive the car yourself. And then we have security. So facial recognition in airports. If you heard things about social credit in China, facial recognition is used in that. It's also used in other various security camera purposes. Image video retrieval, and another reason why it's so important is that digital cameras are everywhere now. Everything has a camera nowadays, so computer vision is more prevalent than ever because it can be used on anything. So here are some applications. Face detection in cameras. As you can see, the bottom right, or bottom left for you guys, is that we can see that it uses face detection and then applies an algorithm when a face is found to make the light darker so that we can actually see the person's face. This is a blending of image processing and computer vision. We have biometrics, so such as reading a picture of a fingerprint or facial detection for logging into your computer. There's also things such as like Face ID and stuff like that. And then we have OCR. This is a big problem that has already been solved multiple times over, but OCR stands for optical character recognition. And if you have dabbled in AI machine learning at all, this is probably one of the first things you did, was make an OCR machine learning program that could read handwriting and convert it to text. As you can see here on the left side is LENet, which was invented by AT&T Labs long time ago. This is one of the first OCR models. And we see on the right is a license recognition program. So if you've ever gone through things like tollways and maybe police, this is how they get your license plate, so they know where to send you your toll fee. And then another thing is automotive safety and self-driving. So as we know, Tesla's cars, very big on self-driving. We have the different levels of self-driving from level 1 to level 5. And we're trying to get to full autonomy where you don't need a steering wheel and you just tell the car where to go and it goes there. That's one of the big things that's being operated on by like Waymo and various other companies. So one of the big things is that computer vision is very interdisciplinary. So as I can see, we can see parallels in neuroscience, robotics, information retrieval, machine learning, and speech. It crosses over everywhere from hospital records trying to diagnose pneumonia from an X-ray or breast cancer or any type of disease in your eye to industrial applications where we talk about preventing bad goods going through, to physics such as recognizing different stars or different planets or black holes. So it's prevalent in everyday use, so which is why it's one of the most important fields of artificial intelligence and why you guys are here today and learning about it. So the main problem is that we want to make a computer understand images. And we know it's possible because we ourselves do it. We can understand what we're seeing every day. I know you guys are people. I know this is a computer. I know this is a water bottle on my phone. But how do we make a computer do that? So if we see in the diagram over there, we can see that our sensing device is our eye, and then our interpreting device is our brain. But we have to parallel that to a computer with a webcam and an actual computer and make it still come to the same interpretation. So some specs about the human eye: we have 10 to the 8th power sampling elements. These are known as rods and cones. These are what sense light and process it, sends it to your brain to be processed. Spatial resolution: we have over 150 degrees field of view from left to right. So if you ever heard of peripheral vision, that's also included in this FOV. We also have intensity resolution, 11 bits an element. So if your view was to, per se, a pixel, this would be the amount of intensity of color and all the information that comes through in each pixel. And then temporal resolution, 100 milliseconds. So your eye scientifically runs at 10 hertz, which is kind of, it's not how it actually works, but when scientifically speaking, this is how it works, and we can see things in motion. We are perceiving it at 10 hertz, but obviously we know motion blur exists, so whenever we wave our hand, we can't see it individually going, our brain blurs it. And 2 eyes can give a data rate about 3 gigabytes per second, which is what our brain processes, which is kind of crazy because our brain does all this other stuff, but also interpreting what we process by these 3 gigabytes a second that we get in our brain. So now that we have a little introduction about computer vision, one of the main things that I want to talk about today is MediaPipe Hands. So as you know, this workshop is for interpreting American Sign Language with computer vision. This is one of the main proponents of that. So how does MediaPipe Hands work? Also, MediaPipe Hands is a basic hand tracking library. There's 2 steps. There's a palm detection model and a hand landmark model. So we're going to talk through this for a bit. So what is it? So MediaPipe is a high-fidelity hand and figure tracking solution. It employs machine learning to infer 21 3D landmarks on a hand from a single frame. So it plots 21 points on your hand, and it plots them in 3D space. So no matter what rotation your hand is in, it still is able to see. And one of the most important things is that it achieves real-time performance on a mobile phone and scales to multiple hands. So one of the big things about computer vision is not only whether it can do it, it's how fast it can do it. Because nowadays, if you think about it, computer vision on a single image is not that bad because we have theoretically infinite time to process that single image. But whenever we're processing a video has specific frames per second that it runs at, has a specific hertz. And so if we think about it, we have a 30 frames per second video in a second. So there's 30 frames per second. There's 1,000 milliseconds in a second. How many milliseconds does that give us to process each image? That gives us 30 milliseconds to process each image. 33.33, blah, blah, blah. But 30 milliseconds to process an image, that means you have to write a program that can read in the image, make sure that it can detect all the features, do region boundaries, all this stuff, and make sure that it can do it in 30 milliseconds. That's one of the main problems of computer vision, is not detecting, because that's a problem that we've been working on since the olden days, detecting things and boundarying things, but how we can make it run on modern day hardware with the advanced cameras we have. So that's why this is one of the biggest things that we do, is that it achieves real-time performance on mobile phone and scales to multiple hands. So it's allowed to track multiple hands, which adds another factor, because instead of tracking one hand, you're multiplying the processing power by 2 that it takes. And so that's just a really crazy thing that they were able to figure out. And so we're going to talk about how they figured it out. So the first step is explaining the palm detection model. So it is very challenging to detect hands. There's a large scale span, so that means there's a lot of difference between people's hands, right? Some people have very small hands, some people have humongous hands, right? Long fingers, different proportions. And another thing that we don't think about is occlusion of hands. So unlike a face where you can look around, there's no really movement in your face. One of the big things about your hands is that you can use your hands to cover itself. So in this case, I'm blocking my palm, so the computer can't see it. or if we have this case where my hand is turning away, it still detects the palm of my hand, but it's not able to see where the fingers are. So this is another challenge that is brought forward by hand tracking, is that this is a thing that we don't see in other places, that due to the placements of our hands, the rotations of our fingers and stuff like that, we can actually block our own hand from being seen by the camera. So that's a problem that we figure out. And another one is that faces have high contrast patterns, hands do not. If you look at a face, there's a lot of features in your face. Eyebrows, the contours of your eyes, contours of your cheek, your nose, your hair, all this stuff. On our hands are pretty plain, right? I mean, there's a couple of lines, but like that's not noticeable enough on a camera if you're on very low pixel density. We just see 5 digits and a palm. So this makes it extremely hard for a computer vision thing to latch on, because they can't interpret like we do. We can't just be like, oh, this is a hand, because we know what it is, we know what it looks like. Computers can't do that. It works off of features and lines, and there's barely any features on a hand, so it can't really extract them as well as we could a face, which is much more complex and more able to get identified by computers. And then another thing is that it requires extra context, such as an arm, body, or person features. So as we were talking about our face is easily identifiable due to the amount of features we have, but because of the simplicity of our hands and the context of rotation, so we can't really like bend our head 360 or like flip our head upside down and like contort our neck in crazy ways, but we can do that with our hand, right? We have a whole free range of motion. So we need to require extra context of it being attached to our wrist and it being attached to our body and all this stuff, so that we can figure out how to track and recognize this hand and track each individual digit, and also recognize that each finger is individual and which finger is which. So as you can see, there's a lot of things that we have to think about that we don't really think about normally, because we're like, oh, that's a hand, it's that easy. So these are just some of the things that we have to think about, and this is also prevalent in all computer vision and a lot of things, and in machine learning in general, is that you have to think about all the problems that we have, because for us humans, it's really easy to see something and say it is what it is. But for a computer, it is very hard, because we don't know how the human mind works. And so that's why we have to do all this stuff to be able to figure out how to do it on a computer. So the palm detection model is called a single shot detector model. And if you want to read the paper, because I know some people like reading papers, I know I do myself because it's really interesting, I would take a look. Even if you're like frightened by reading papers, I think I was really frightened by reading papers. I was like, there's a bunch of graphs and math and like, I don't know what it means. But if you actually take a deep dive in and just read some of the famous papers, like such as YOLO or SLAM, or maybe one of the OG like neural network papers, I recommend you guys do it, because you learn a lot. And even if you don't understand it, you can watch postmortems by other people and read like summaries and stuff. But I really recommend you guys start reading machine learning papers. That's one of the best ways to learn artificial intelligence machine learning. Anyway, so why it's called a single shot detector model is that it takes a single shot to detect multiple objects within an image. So like it just uses one picture. But so like everyone's like, oh, why is that so important? The reason why this is so important is that because the previous method required 2 shots. And if you think about it, if we only have 30 milliseconds to process an image, by going from 2 shots to 1, we're literally halving the time it takes to able to compute what is a hand and track a hand and all the individual joints, right? So this is truly a breakthrough. And the reason why it needed 2 shots for the old version is that there were it had to generate region proposals. So what is a region proposal? If you have a hand, a region proposal is a box where it thinks a hand is. So you would have a bunch of region proposals, like maybe it think like this little line on the whiteboard was a hand and stuff like that. It would generate a bunch of region proposals, and then it would detect the object within each proposal. So then once we know this is a hand, and then we run it through the detecting the object, if it was this line, it detect like that doesn't matter, so throw away the region. But if it is a region with a hand, we're able to do more in-depth analysis, because then we're saving time, because we're not in-depth analyzing the whole picture. We're only analyzing the small region, which saves on compute time. It also allows us to create the individual finger tracking and palm tracking within 3D space. and just tracking the ligaments in general, because we're specifically focusing on that region rather than the whole picture. This not only limits compute power, but it also increases accuracy of tracking the hand. So that's why it's kind of crazy that this new model that only takes one single try to do the region and the hand finding, it's significantly lower compute times, and it's one of the main reasons why we're able to do things that we can do today. And just these observations, because this paper was founded in 2016. So in the 4 years that passed, there's probably way more better methods or different methods that can increase compute time. So that's one of the major things that machine learning researchers do, is not only how to detect stuff, because the problems on how to detect stuff has also been solved, right? We've had machine learning since 1960. So all the problems like, is that a chair? Is that a table? Is that a blank on blank? Has already been solved in like 2010. One of the big things is making these models more efficient. That's the problem now. Another problem is data. The data that we process to collect for these models is one of the big focuses that we have now, because models have already existed for tens of years, and we've already experimented with all of them. So that problem has basically been solved. So one of the questions you might be asking is why we detect the palm instead of the hand. So one of the reasons is that the palm is easier to identify, because fingers, like this is a set of fingers, and then I can close them, and that's another set, or I can slightly open them, or open some of them, or like cross them, and stuff like that. So all of this variability just adds extra hardness for us to track and render a wireframe over fingers. So another thing is that it's a smaller object. So our hands are kind of big, and there's also a lot of variability in finger length and stuff like that, and finger spacing. But palm size, there's less variability, especially in the way it looks, because if you look at all of our palms pretty much look the same, right? Like it's basically just like a little square. But if you look at each other's fingers, you'll see a wide variability in the wideness of our fingers, the length of our fingers, the different lengths of the joints. So this just requires more brain power that the computer has to use to figure out whether it's a hand or not. So we try to make it as easy as it can for the computer to figure out whether it's a hand or not. And another thing is that the palm, if you look at your own palm, it's shaped like a square. And that allows us to use simpler bounding boxes. If we were able to take our hand, think about all the different shapes we would need to block off our hand, right? So we have our palm, right? And then we have like maybe a bunch of different squares for each of the fingers. And all this extra processing time to find the fingers and box them out just takes more away from the 30 milliseconds that we have to figure out whether this is a hand and track it. So that's why we try to make things as easy as possible so that it's faster. And not only is it faster, but it makes it simpler so that it's more accurate. And then another technique that they used to faster detect these things is called an encoder decoder, and also known as an autoencoder. This is something that you'll experience maybe later in machine learning career if you happen to go really heavily into deep learning and computer vision. It composes of an encoder and a decoder, as it's in its name, where the encoder compresses the input. So in this case, we get image. And what compressing does is it basically just lowers the pixels. And what the decoder does is it attempts to recreate the input from that compressed image. And what this does is it helps with feature extraction. Feature extraction is a thing where we try to extract different features. And let's take, for example, our face. Features could be the defining line of our eyebrows, right? We all have like this underbrow line, or the length of our nose, that line, the feature of that, or the feature of our mouth or our chin. And compressing and decompressing allows us to make the machine learning model learn from these low fidelity images what is most important. So when we compress these images and turn it low fidelity, we make it focus only on the most important elements because there's only so many pixels we can give when we compress the image. And this is especially useful on hand because, as earlier we talked about, feature extraction is very hard on hand because of how simple it is. And so that's one of the main reasons why we use an encoder decoder. So all these techniques added together help shorten processing time and gives an average precision of 95.7% in palm detection. This means out of every picture of a palm, the machine learning model will get it 95.7% right. Technically in a time, that's not really how it works, but in reality, it just means if you short a palm, it will know it's a palm and it will know how to block it out. And it also does it very fast, so you can use it on low power computing units such as like a Raspberry Pi or Arduino Nano. All these types of ARM chips, you could be able to utilize it on that. And you don't need like a beefy gaming computer to run your little hand detection algorithm. So that was only the first part that we employ in that. You have a question?
Yeah, I had a question on the previous slide.
Yeah.
It looks like you're trying to make things run faster.
Yeah.
Is it possible to eliminate the decoder step entirely and have the brain digest just an encoded file?
Yeah, so you're saying the encoder decoder, just like remove it?
Right.
So yeah, so you could remove it, but one of the main things that encoder decoder does is it allows us to gain more accuracy. So a big part of this is that you have to determine what you're willing to sacrifice in compute time for accuracy.
Right.
So that's just a big like give and take that you have to figure out. And I don't know what the numbers are without the encoder decoder.
Patterns. I mean, I would imagine the pattern would still be there even with an encoded file.
Yeah, so the pattern will still be there. The problem is that for us, we can see the pattern, right?
Yeah,
for a computer, it's infinitely harder for it to decipher.
It's just a different language for them to recognize.
Yeah, it allows us to it allows the computer to easier pick it out. So not easier, but more accurately. So on multiple pictures of a hand, maybe without it, it won't pick up some of the features, and so it won't be able to detect the hand. But if we use an auto encoder, it allows it to be more accurate. Even though we are sacrificing some time, obviously the engineers of Google figured that the sacrifice was well worth it for the added accuracy it gave.
Yeah, I mean, if you guys got it perfected, then no need. But like, if you guys try to save some time, I mean, that would be a step, you know. Like,
yeah, there's a lot of steps and stuff like that, but obviously, whenever they're planning this out, they thought it was well worth it. And then this brings us to the next point, which is the second half of this thing, which is called the hand landmark model. So this is how the hand is tracked. And these are the points that are put on the hand so that it can recognize it as a gesture. So what the hand landmark model does is it performs key point localization of 21 3D hand knuckle coordinates inside the detected regions versus using regression. Regression is, of course, the thing you guys heard about, which is like machine learning regression using convolutional neural networks. That's how they apply the fingers. And it's robust to even partially visual hands and self-occlusions. So as we talked about, your hand can block itself off. And this is robust to that because it has been trained on so much data and so many hands that it's able to guesstimate where your hand will be. So in order to train this, to get the ground truth model, it required the manual annotation of 30,000 real-world images. So that means out of 30,000 images, people had to go through 30,000 images and hand label the 21 points on each hand. So that's kind of a pain. But this is the truth of a lot of data processing in artificial intelligence, is that we have to do it by hand, and you have to do a lot of data. So this is just one of the interesting things behind this, is that these researchers had to literally just go through picture by picture, plot 21 points 30,000 times, and like that's kind of crazy, is to get the data in order to make this accurate model. So let's look at the whole pipeline. The whole pipeline is here, and this is this might look really confusing, but if you ever become a machine learning engineer or a data scientist, this is one of the main things you'll see whenever you're talking about models. So it's really important that you guys get exposed to this early so that you can understand what it looks like. So if you can see that we have the input frame from the graphics card, we transform it, and we can see that hand landmark is right there, and we have palm section right here, and then we have the final renderer, which renders that little wireframe skeleton hand on your actual hand at the end. So this is the whole process. And if you want to see the rest of the thing, we can go right here. I guess I'll just go to it right now, but if you want to check it out on your own time, you could check this out. This outlines the whole pipeline for all of this. So we're able to see the what the output looks like. This is how the output is calculated, and we can also see. Let's see, not hand detection, hand tracking. Okay, well, I think it's kind of scuffed on this computer because the resolution is kind of low, but it allows you to see. Oh, here we go. No. Oh, here we go. So we can go into the hand tracking model, and this is how they do hand tracking. We can see that it does image transformation, and then we see it goes into TF Lite web GL interface, TF Lite sensors to detections, and then we can see non-mass suppression. And we can see that all of this is explicitly laid out, and this is how real-world machine learning engineers do it. This is how they document their models. And it's kind of crazy to see it, and this is something that I would recommend looking at and maybe even trying for your own pipelines and your own applications if you happen to create them. I'd recommend creating some useful documentation diagrams. So onto the main thing of this presentation is called American Sign Language detection. So how do we do it? One of the main things is that if you think about it, American Sign Language is just a gesture. Like if you ever use like HoloLens, you like pinch things to move around in 3D space. American Sign Language is basically that. It's just a bunch of different things. So Y, V, W. We just need to recognize these stationary gestures and convert that to English text. So how do we do it? We use a data set of labeled ASO letters. So there's a Kaggle data set with cut fingers. Let me show you this. So we have this, and we basically just have a bunch of pictures of just random people's hands with the corresponding number in American Sign Language. Then we run MediaPipe over that data set, which helps us generate the wireframes. And specifically what we want is the coordinates of each joint within the hands, right? So if we have this, if we have the coordinate of each joint in the hand, we're able to classify it, because if your hand goes to the same position as this, because it doesn't change, then we can classify it as V or W or Y, right? So, and then the next thing is we train a machine learning model over those coordinate points so it can figure out if you're in the same one. And then the last one is apply model to real-time coordinates from MediaPipe. So whenever you use a webcam, that would be the actual thing where you can do the different hand signs and stuff like that. It's really that easy. Like, this is not that many steps, and it's not complex once you get down to it. But the main thing is just understanding all the little steps that go into it and just executing them so you can do stuff like that. So the problem is that we don't have a demo. The reason why is that we are applying to receive a research grant for this from UTD. So I'm in the process of drafting a research paper right now for this. So we don't actually have a demo right now. But the demo that we do have is accessible right here. So if you want to go on your computer, access this, make sure you have a webcam, give it webcam access. You can test it out yourself and look at all the very cool things they can do. And I'm going to pull it up here. So one of the main things is that you can just hold up your hand and it tracks it. And we can see that in the 3D graph view right there, we can see that it shows the wireframe of the hand, and no matter what position we do in 3D space, as we can see as it rotates around. And one of the cool things is that if we take our hand, form it into a fist, and point the fist away, you can see that it's still kind of tracking it, which is extremely cool, because that means it's guesstimating and knowing that we put our hand in a fist, and even though it can't physically see our fingers, it's still tracking them. So this is really cool because if you do things like point to one, and then we put another object over it, it can still, we can see that we force it into a fist, right? But like if we have all our fingers up, we can see that it's guesstimating kind of that it's a fist or like it's in front of it. So it's really cool in the way that it's able to decipher and figure out that the hand is being occluded by something, but it still exists behind it, or it's in a different form and it's just being covered by itself. But while we still can't see it, it's still there. So this is one of the cool things that we test out, and it's extremely fast and accurate. There's also some other things on here if you want to try. If you just hit MediaPipe in the top left, you can do things such as face mesh. So if we just load this up, we can see that actually tracks the face. As you can see, I'm wearing a mask. So even though it can't see my full face, it's still tracking my full face because all the training on data it's done and the similarity of human faces, it's still able to put a mesh on my face. And then we can also do this to full pose tracking. So if we go here, we're gonna do holistic, another full page view. I don't know if this will work, but so if you ever done things like Connect, if you ever play Connect games or like, I guess Wii games to an extent, this is what they do. They basically do full body tracking, Just Dance, you just dance. This is how they do it. And it's really cool. And I don't know if it'll load, but basically there's a lot of applications for this. A lot of applications that are just emerging now. One of the main things that I've seen is a yoga app where you point the camera at yourself and it actually tells you where you're going wrong with your yoga app. I mean, where you're going wrong with your yoga form. And there's also things like weightlifting, so like doing bicep curls and stuff, or doing squats and stuff with a bar. It tells you what's wrong with your form using machine learning and computer vision, which is honestly really cool. And I would recommend you guys experiment with this technology yourself and see all the different implementations you can do, like creating a game, or maybe doing like, there's another one where it uses artificial reality and this kind of tracking to teach people what's going wrong with their basketball shooting form or their golfing form. And there's all these different implementations that I would suggest that you guys go find out yourself, because this is such a new technology, it hasn't been discovered before, and maybe you can have the next great idea that can get you $1 million. But anyway, it seems like it's working kinda. Not really. It might be too strong for the computer, but let me try again. But yeah, this is just a really interesting technology that I want you guys to go and check out, MediaPipe. There's a lot of different other technologies I can check out, and there's also a lot of different demos you can check out. So as you can see, it's running at 1 frame per second, and because this is doing whole body tracking plus face tracking plus hand tracking, the computer might not be strong enough to do all this. So I don't think it's gonna work, but you can understand it. I guess it broke. You can understand the type of power that this type of technology has and the different uses that it has. And that's basically it for this workshop. So thank you guys for coming out, and I hope you guys learned something and maybe you'll apply it yourself. This is the checking code for membership. So if you're a member of AIS, you will know if you are one because you sign up for it and got an acceptance letter. Just follow these instructions. We have a whole new membership portal by our tech team, and it works. And it's better than ECM's. But yeah, make sure you check in. And then if anyone has any questions, I'm going to be here for a bit, make you some snacks. Yep.
It's saying wrong code.
Okay, well, send you.
Okay, I'm gonna try to fix this. Give me a second.
Guys, that's not my problem. I'm on the content team. I only make workshops. Anyway, yeah. So if anyone has any questions or anything they want to talk about, I'll be here. Thank you guys for coming out.
Are the hand models neural networks? Like that's how they train it?
Yeah, so they're trained over the images. And so Google already trained it for us, but if you want to make your own, you could if you wanted to.
You mentioned that GitPod was the place to go look for some AI libraries and that this place has some, but these seem very useful. I mean, I could see people using these libraries.
Yeah, a lot of people use these libraries. If you ever,
We'll have even more.
yeah, there's a lot of them that exist out there. You just have to look for them. I know, like places like Snapchat, they have their own proprietary version of it.
Yeah,
Making Snapchat filters.
Yeah, they do their stuff.
Yeah.
TikTok will have that.
Mhm. Yeah, so there's a bunch of stuff that you could do with it, and it's just really interesting.
Yeah, of course, yeah.
Is there a code online or is that one?
If you have to go, I'll just write the code down.
Oh yeah, if you remember, just have the code down. We'll open this code until end of tomorrow, so just keep checking. Either that or we'll send out an announcement, yes, on our Discord if you're not on there. So yeah, 0203. We'll figure it out by tomorrow. Thank you guys. Yeah, if you guys want to steal some chips, I'm about to eat it after tonight, so please steal it.
You try to make a game for it.
Yeah. I think you mentioned something about all this is funded, somebody funding you.
Maybe we're trying to make a grant proposal.
Well, and then how do you do it? Do you go to a certain company or?
Yeah, so usually actually have some programs for undergraduate students funding, but if you actually have the things that you're getting funded for, that's not really hard, like that can't be funded by the university. Like I don't get what you do around $500,000. If you're trying to look at $50,000, a lot of things, everything just and it's like,
Yeah, I don't want to go, like if I have like a project I'm working on, but I could create a fund.
yeah, so you would just have to get money from various sources. Yeah, so you have to look through a bunch of stuff, so maybe like asking companies, some companies do sponsorships, or like grant
But who would I talk to? Is there like a fund negotiator?
that varies on company by company.
Okay.
So yeah, it's a feature we can work
Like,
on.
right
Right
now,
now,
for
there's a
example,
lot
if
of
I have a
issues.
project and I'm working
We're trying to figure that out first. Yes, that's involved. So hopefully by the end of this semester, you'll be.
Oh, so you're saying like you have a contract, yeah.
Yeah, I'm working on, but I need help, and I'm willing to pay some money.
As a company, you just have to like think about like just like hiring people, like stuff, like maybe posting like job offers and stuff.
Yeah, but is it like you go to the grant system?
Yeah, so, that was big.
Yeah, I go to the university.
Like, we just want to.
Undergrad, but
University.
I reached out to,
Workforce.
Oh,
Yeah, that's why I have this.
So there's probably like contact, I don't know, there's probably like, yeah, there's probably some, yeah, there's probably an office at UTP.
But how did the company find you?
Oh, I had to do myself, right? I had to go out to the university, like, I had this proposal.
Most of the time, we're proposing to the university.
Yeah.
We have to go down to the corporation.
Yeah,
I'll take it.
I'm going to the university.
You go to the university.
Yeah.
From the student to the university.
Yeah.
You say, hey, here's my plan. And then the uppers in the university decide whether or not you get the grant. So you get the grant through the proposal to the university.
Yeah, and then if they accept it, I get money, and then I talk about it, like,
Correct.
So for me, I'm like,
Well, I guess.
I'll talk to the.
Yeah, so I would probably,
To say like, is
Yeah.
yeah, they took much out.
The university directly.
Yeah, there's probably an office, I look like UTP grads.
So if they would be the section of the CES department, it would be directly to the university.
Yeah, I mean, if you ask anyone like CS or like anything, they're probably good at UTP grad place. Cause like UTP loves like people who probably like.
Yeah, well, I don't know how it works, I really like. Then I'll do it all day.
Yeah, I know.
Like, I don't know, like, is that public chat.
Yeah.
And that kind of.
I would definitely reach out to you. Yeah. I would definitely talk to you about that.
Okay, talk directly to you too. Okay, got it. Thank you for coming. Send me an email. So, if I have any question, I can ask.
Yeah.
Okay.
Oh, you're Alpha.
Yeah.
Nice to meet you.
We talked
Yeah.
about chat a few times.
Yeah, thank you.
All right, thank you.
Hey, I was wondering if you have a link to this presentation, like a
So do we post the links to presentations on the AIS website?
Yes, usually we do slides like.
Okay, yeah.
Usually we put it after workshop.
Do you know our website? It's ais.uc.org, and then we have like a workshops, events,
Our events tab,
and then the event will be there, and then we'll pay for stuff.
Sweet.
Yeah.
Thanks.
Thanks for coming.
Thank you for having us.
Yeah.
It's been nice to shit things, like confusing.
Yeah. We're working on it. There's some quirks.
But yeah, we have a lot of technical issues.
There's some quirks in the process.
Yeah.
Good God, you guys like, you have, if you want to be a member, you have to do this.
Oh, no, there's no like requirement to be a member.
That's what I thought, but I mean, I haven't been in anything like 3 years, so like, maybe something has changed, I don't know.
So we do have a new membership program. To get it, yeah, so everyone applies, it's free.
What kind of membership is this?
It's just more of like,
Is this the AIS membership or is there something different?
this is like, guys.
Okay.
Our organization.
Or the organization, the infrastructure of the organization membership, it's not for like, and not everybody that's interested in AI needs to be a member.
No, of course not. It's just more of a tailored experience for those who seeking.
I think we need to name our members something different.
What's that?
We need to name our members something different. People get confused because like if you come to an event, technically you're like a member.
Well, see, that's we're trying to break it. Like saying like if you just come to an event during this you're not really technically a member. It's like a more official
It's
definition.
like an AIS staff. Is that what it is? Staff.
AISers, AIS heads.
Answers, sounds terrible. Regulars.
Oh yeah, regulars. That's pretty good. Yeah, because I know a lot of people get confused. I get a lot of messages about it. They're like,
But is there any advantages to joining up and not, or?
Okay.
Supposed to not be one?
Product accomplishment?
Well, aside from a resume boost,
Okay, cool.
you get perks.
Cool. Oh, we're not for it.
member
So one
only.
thing is, we have member exclusive events, member only events.
All right,
Yeah, AIS exclusive merch for members.
sweet. What are the prerequisites?
There's no prerequisites, just have a small application form and like ask for your
So
details.
anyone can join? Anyone can join?
Well, it's only for the to students. It's not only UTD, it's not like anywhere like outside of college.
Where is not UTD?
What's that?
Where is not UTD?
Unfortunately, COVID. Outside of UTD.
So I can't join if I'm not UTD.
That's correct. That's a sad truth, but since we're just like.
Good job, Aaron.
Can I still go to the event?
What's that?
Can I still go to the event? Yeah, I know. I mean, that's why I say, you know, what.
Majority of events are open to public.
You know, yeah, I love going to events. I think you learn a lot more from events than you do online. But I learn a lot online too, you know.
Yeah, exactly.
But events are not like, they build relationships.
Someone asked, I registered but didn't get a confirmation. Is the confirmation delayed?
For what?
Probably this. Do you get a confirmation if you sign up?
Yeah.
Yeah.
Oh, I actually work for me right now.
0203?
0203, same code. I think you'll fix the issue. If you untry it on your end. But yeah, when you sign in, it literally just says checked into and it's like check mark.
If they have problems, where should we direct them to? Do you have like a support channel?
We have a membership channel in Discord. So I'll just send a